Well, welcome back, guys. Week number 2. All right. Um, the plan for today is we'll finish up chapter 1. We'll definitely get into chapter 2, probably about half of it. Then on Thursday, finish up chapter 2, and then obviously get into chapter 3. Now, we may depends how we get come along. Right now, we're scheduled for what, the 11th or the 10th, I believe, of September for the first exam. That is a little bit flexible. I can move that back maybe to Wednesday or Thursday, but it all depends on how far we get along. So we'll see what happens on Thursday. All right. Any questions? Everybody know where to get their stuff, right? Everybody knows where you get your textbook and where the homework's at and everything, right? No surprises, right? Okay. Okay, well, we stopped right here, slide 24, and we had just finished talking about physical and chemical changes. The main point, the main takeaway from all that is this: a physical change, the chemical structure of the molecule or the compound did not change. It still remains the same before and after. Unlike a chemical change where you essentially take the compound and break it up into something new, into a new compound, back to the elements, anything of the sort. But change it completely. That is a chemical change. Okay. Now, granted, we went through these examples. We're not familiar at this time about the structures, but at least I want you to analyze the chemical equation, like number 1 here, where you saw NH3 beforehand, that's before the arrow, and it still is NH3 after the arrow, okay, to the right of the arrow. So that tells you a physical change, unlike number 2, where NH3 gets broken down into nitrogen and hydrogen. Okay. Now, elements, one type of atom only, and they can't be broken down any further. As you break them down, they become the subatomic particles, of which we're not going to talk about, other than to say that those subatomic particles will be either the proton, neutrons, and electrons, but more on those later on. With respect to compounds, they are defined as the combination of 2 or more different elements. Okay, different elements. If it's just a single element or single atom, it's an element. But if it gets combined with another one, hence sodium chloride, 2 different elements, that's a compound. Carbon dioxide, 2 different elements, that's defined as a compound. Okay. Pure is pretty self-explanatory. All the particles are the same. There's nothing else to separate. Okay, it's just pure whatever that material is, as compared to a mixture where you got 2 or more different particles, different elements, different compounds. It could be different elements or different compounds or any combination thereof. Now, if we look at this diagram, a couple of things here first that we can look at the diagrams. You'll see a lot of these diagrams to kind of depict atoms and mixtures and all kinds of things, but they're defined as the spheres, how we have different colors. Let's go down here to the bottom left. You can see here that we got these spheres, circular material that is all one color, all the same, okay, as compared to the one next to it, where you can see that 2 of them are essentially combined together. Now, we're going to learn about this, that there are elements that cannot exist by themselves. They have to exist with another one of the same, and those are called diatomic elements. Okay, they're both the same. If they're both different, then they're compounds. Okay, but the 2 colors and the 2 sizes represent 2 of the same elements. If we look at the next one over from the left, looks like Mickey Mouse ears are sitting there. Okay, you got the red circular sphere, and then you got the 2 yellow ones. what that represents are two different elements. Now you can have 1 to 1, 1 to 3, 1, 2 to 3, any combination thereof. But they're different elements, and that represents a compound. Okay, a compound. I'll come back to that. So, and then the next one over, again, two different elements, two different colors. That represents another compound. Okay, so we got matter up here. And if we go to the right, we're talking about a mixture. I think this is pretty self-explanatory as any mixture. If we look at here, we got basically a mixture of two different elements. And how would I know they're elements? Well, look at the dark ones. That's all it is. Dark ones, they're by themselves. Now, a note about those that are combined together. We call those diatomic, two atoms, okay? We're going to learn that of the 118 elements, there's only 7 of them that exist here on Earth at 25 degrees Celsius as diatomic elements. Right now, we don't know what this is. All you can say it's an element and it's diatomic. So we got a mixture here of two elements. Now, if we look the one on the right, it looks like we got a mixture of 3 different elements, okay? 3 different elements. And what we got here is examples that represents, could be neon, a single element. This O2, notice here O2, AKA, as we know, is oxygen, but it's diatomic. You'll see that we put oxygen and then we put a subscript, okay, after the O. That tells us that there's 2 atoms of oxygen bonded together. It's diatomic. We're going to learn that hydrogen, H2, is also diatomic, okay, with 2 elements of hydrogen. All right, so mouse has been acting up today. So these are diagrams of a mixture of different components and diagrams of pure material, pure substance, either of an element or a compound. Now, examples of mixtures. We tend to think that, we look at iron, if we think about iron, pure iron is a very soft material. Yes, steel is iron, but steel is a mixture with other components in it to give it strength, because pure iron in itself would not be strong enough to use to build buildings. The same with gold, pure 100% gold, very soft material, not very strong. So the jewelry that we utilize is really a mixture with gold and different components in there. Brass, for example, is a mixture of zinc and copper to give it that property. Sand, granite, all mixtures. Tap water, definitely a mixture, because in that tap water, we got a variety of components dissolved. We got all kinds of salts in there, and plus organic material, just a big old mix. Same is true with air around us. We got a mixture of gases, nitrogen, oxygen, so on and so forth, okay? Compared to pure substances, if we take sodium chloride, purify it and clean it up, and that's one of the steps every time we make compounds. We make a new compound, it comes out dirty, and we have to go through various steps to purify it to get it pure. But sodium chloride is it would be an example once it's been purified. Diamonds, 100% pure diamonds are kind of rare. They're normally the diamonds we find have a little bit of other material in there, other metals that give it a different color. But yes, a pure diamond is made up of nothing but carbon. If you could find one, it'd be very expensive. Distilled water, it's basically nothing fancy. Is you take tap water and you boil it. You have a condenser. I don't know if you've ever seen a TV program, the Moonshine program, where you have a steel, they're heating up the material to get the alcohol off of the mash they made. Well, distilled water, that's what you're doing. You're taking water, you boil it into a special container, and it condenses and collects it nice and clean. And a lot of the elements that we find are pretty pure, like mercury metal is fairly pure. Again, here's some more diagrams. to demonstrate or to depict a variety of different combinations. The one on the left, when you see that diagram, you can see, hey, this is a diatomic element. And it's pure because that's all we see. All we see is the white circles there, and they're combined together. There's two of them, so it's a diatomic. It's all you can say about it. On the middle one, it's a compound. Okay, I think to remember about compounds is that there's always going to be a central atom, and then other things are bonded to that central atom. So in this case here, the white one is the central atom, and then these gray ones are bonded to the central atom. So this could be any combination, anything. It could be an example of carbon dioxide, for example, where the white one is carbon in the center. But again, it's a pure mixture. It's all you see is that particular compound. And finally, on the right-hand side, you can see we got a mixture. We got an element here of one color, and then we got another element here in the darker color, and then this Mickey Mouse ear kind of scenario here. Again, you can see it's a compound where that gray is a central atom, and then the white ears could be any multiple of things. This could be, for example, water, H2O, where the dark represents the oxygen and the white ones represent the two hydrogens bonded to that. So these are just general diagrams that we utilize to depict an element, compound, mixtures, so forth. Okay. Now, for example, if we take a look at A, obviously we can see there are two clear spheres bonded together. And that's all there is. So all we can say is it's an element, specifically a pure diatomic element. The same, similar with B, we have a dark center with three white ones bonded around it. So it's a compound. Nothing else in there except those species. So we got a pure compound. C is the first example of a mixture because you got the clear and the dark ones. So it's a mixture of two elements. That's what C is, just a mixture. D represents, again, an element of some sort. Okay, we're not asking here to say what is it exactly. Well, we don't know. It's just a diagram to depict a pure element. And that's D. E, again, we have a compound and nothing else. And so we have a compound, pure compound. F is another mixture. It looks like mixture of two compounds and an diatomic element. Okay. And then G, obviously, again, a mixture of a element and a compound, and then H, just an element. And if we can even deduce that H probably represents a solid just because it's nice and ordered compared to the other examples. All the elements are nice and ordered. Okay, I think about the elements. We're going to talk about those. Let me pull up the periodic table. We're going to utilize this periodic table quite a bit. Okay, so we have 118 elements. Every element has a symbol and a name, okay? And every element has a number, an atomic number. And we're going to be able to gather a lot of information from that atomic number. So let's take a look at beryllium number 4. Its atomic number is number 4, okay? Its symbol is Be, which is beryllium. And then there's a number, a decimal number underneath the symbol. That is called the atomic weight. Notice that every one of them has a different atomic weight. Now, the other thing to take away from the periodic table is on top of each column, okay, we have two types. We got ones that are labeled with the A, Roman numeral A, and some with the B. So notice that we start off with Roman numeral A, 1A. Everybody in that column has a specific property we're going to talk about at length. The same is true with Roman numeral 2A, a very specific property, okay, in Roman numeral 2, and the same is true for Roman numeral 3A all the way across to 8A on the periodic table. The B's, we cannot talk about the specific property because they vary, but it's very specific for the 8 elements for right now. Now that number, the atomic number, gives you some very 2 bits of information. We're going to talk about protons, neutrons, and electrons. So that atomic number 4, for example, tells you that there are 4 protons. So element number 1, 1 proton. Element number 118, 118 protons. Okay. It also tells you, with respect to a charge, and we're going to be talking about these charges, all the elements on the periodic table have a net 0 charge. And so not only does it have 4 protons, which happen to be positive 4, it also has 4 electrons, which happen to have a negative charge. So a +4, a -4, guess what the net is? 0. Okay, net 0 charge for all these elements. And you can also guess that the horizontal, if I go in that direction horizontally, across the periodic table, these happen to be different levels, energy levels. Think of them as like the onions, the layers of an onion. You got the first layer starting with hydrogen, and they go all the way. There's 1, 2, 3, 4, 5, 6, 7 layers. 7 onion layers. And guess what? As you go down the layer, the atom gets bigger. So you got your first trend that you can get from the periodic table. So if I want to compare the size of, say, sodium, which is number 11, and compare the size to potassium, which is number 19, I can say, based on where potassium is at, the potassium is bigger than sodium, just by its position on the periodic table. Okay. All right. So these are all the elements, 118, and they are working on more, by the way. Working on more. Now, before I leave the periodic table, this table hasn't been updated yet. It will be in the future. But if we take a look at these, it has some strange letters as names. 118, 117, 113, and then the infamous 115. Those have temporary names on them. They have been named since then. Those guys have been, 3 of those were made, 2 years ago. They were finally made. Number 15 is, I believe the name they decided on was Mosconium. It was found in Moscow, but it's some infamous. There's a lot of ancient alien stuff going on around element number 115. So FYI, we'll talk about some of the stuff as we learn more about the periodic table. Okay, so let me go back. Okay, so each element has a unique name, a unique symbol, and a number. Okay, now that number below the symbol, that is a number that we're going to use a lot down the road. Now you can obviously get on the internet and you can get all kinds of periodic tables, and that number, that decimal number, can vary. So we ask you that when it comes to calculations, future reference, is to use the number, the atomic weight number from our periodic table, because you'll find other periodic tables have a slightly different number, which then when you use it in the calculation and you type that in Canvas, the Canvas numbers are based on the periodic table values that we give you. And if you use someone else's periodic table, your Canvas is not smart enough to recognize that subtle difference and count it wrong. Which, by the way, if you answer any question, any of the homework, anything like that, and you know yours correct or you're pretty sure it's correct, let me know. I'll look at it. If it's correct, I definitely will give you credit. Sometimes you inadvertently add a space. Canvas is not AI, trust me. Canvas treats that extra space as a wrong answer, which is crazy. Okay, so anytime that happens and you know, hey, this is right, shoot me an email. I have no problems giving you credit for that because Canvas is not the slickest piece of software in the world. All right, so with respect to the symbols, you'll notice in the product table, a lot of them have a single letter. That is the symbol. That letter is capitalized. Obviously, you can't use all the letters before 118. So there are some elements that have a second letter, okay? And that is lowercase. You got to lowercase it. For example, you have calcium, which is uppercase C, lowercase a, cobalt, uppercase C, lowercase o. Why is that so important? Because if you inadvertently write uppercase O, you no longer have cobalt. You have carbon monoxide, totally different chemical compound. Okay, not even an element. All right, so be aware of the symbols correct format. Now, most of the symbols have English names: H for hydrogen, O for oxygen, He for helium. However, there are some that have their name derived from Latin names. Lead, PB, comes from plumbum, which comes from waterworks. And AU is Orium, which means golden dawn. So its symbol is AU. Okay. So be familiar, learn the first 20, and I'll go over them in a bit. But on top of that, start learning these other ones because we'll be using these as we progress, and we'll be adding more and more as we progress. Silver is Ag, Au is gold, as we mentioned earlier. Pb is lead, Br is bromine, I is iodine, and Hg, lowercase g, is mercury. Okay. Now let me run through the first 20 here for you. And so if we go to, for the first one, the very top left, we have, this is what starts off. Element number 1 is hydrogen. And then you go across the periodic table and get element number 2, which is helium. Number 3, Li, is lithium. And then number 4, Be, is beryllium. B is boron. Okay, C, the infamous carbon, very important element. We wouldn't exist without it. Okay, and then N is nitrogen. O is oxygen. F is fluorine. A note about that. Notice I called it fluorine. Fluorine. Unlike what you use this morning if you're using fluoride. Now, fluoride, IDE, is different than fluorine. Just like the one below it, chlorine is different than chloride. We're going to learn that these guys on the right-hand side, when they change because they're going to either gain or lose electrons, and they're going to have to change the name. So fluorine, it becomes fluoride, but more on that later on. Then we have Ne, which is neon. Give me 1 second. I got to let somebody in. Okay. So number 10 is neon, and then we go back to number 11. We go to the left side, and we got Na is sodium from natrium. Then Mg is magnesium. We shoot across to number 13, which is aluminum. And then Si, which is silicon. P is phosphorus. S is sulfur. And then notice here, Cl, chlorine. Okay, in fact, everybody in that same group, and that is fluorine, F, and down in Cl is chlorine. Guess what? Br is bromine, and I is iodine. Okay, and then finally, number 18 is argon. And then we come back to number 19 for potassium. And then finally, Ca for calcium. Okay. Now, keep in mind, this calcium, the element of calcium, is not the calcium that you're ingesting. There's a big, big difference. Okay, big difference. And so those are the first 20. And obviously, we're going to start using quite a bit. We're going to use zinc, Ze. We're going to be talking about copper as we go down the road, and iron sitting right here. And then you got mercury sitting right here, so on and so forth. But we'll get to those as we need. Okay. One aspect about the periodic table we will talk about. I mentioned up here the Roman numeral numbers, 1A, and then we shoot across all the way across down here. Okay. Where we got Roman numeral 8, that's V with 3 I's. I should mention Roman numerals. I understand they don't teach it very much now. So Roman numeral, Roman numerals, their numbering system use letters. So the letter I represents 1. So look at the far left. Capital 1 is 1A is Roman numeral 1 or group 1. Then 2A, okay. And then 3 I's is the number 3. And then the IV represents 4. The I in front of the V, V is 5. That means subtract 1 from 5 gives you 4. And then you go across, V is 5. And then V, if the I is after the V, then you add 1. So it's 6. And then 2 I's after the V is 7. And 3 I's is 8. That's the Roman numeral number, which is interesting because they don't have a 0. The Roman numerals don't have I guess they don't understand the concept of 0. All right, so these guys in the 8A, very special name, those are gases. All of them are gases, very inert, very happy. They don't react very well with anything because we're going to learn that those guys right there, their outermost shell, we're going to learn that the protons and the neutrons are in the nucleus and the electrons are floating around like the solar system. The sun's in the center and then we're all hanging around on the outside where the electrons are rotating around the outside the nucleus at different layers. And these noble gases have a magical eight electrons around it, which make it inert. There's something about the magical eight electrons to prevent that all these reactions all these elements strive to have, and that's what drives the reaction. Okay, they'll all have so except helium's got 2. All right, so we'll definitely come back to that. All right, with respect to the physical states of these elements, 118, this is at certain conditions. 25 degrees Celsius, because obviously the physical state of being on the surface of the sun will be totally different, right? Because it's a little bit hotter. So for a reference point, we talk about 25 degrees Celsius, which is roughly room temperature, and then 1 atmosphere pressure. Right now, we are approximately in 1 atmosphere pressure. As you go up higher, like up in Colorado, that pressure gets less. You go deeper into the ocean, it gets higher. Okay. Under these conditions, there are only 2 liquids of the 118 elements. The only 2 liquids are 1 metal, which is mercury, and 1 non-metal, which is bromine. Okay. The next one, the elements that are gases at 25 degrees are all the noble gases, okay, that I mentioned, that group Roman numeral 8A, there's 7 of them, okay, plus you have hydrogen, which is H2, nitrogen, which is N2, oxygen, which is O2, fluorine, which is F2, and chlorine, which is Cl2. Okay, and so let's do some accounting here. So we have two liquids Okay, and that means there are 7 noble gases on the periodic table. So there's 7, 8, 9, 10, 11, 12 elements that are gases. Okay, so that's, 14 total. We have 118 minus the 14. So we have 104 elements left over that are solids. Okay, that are solids at 25 degrees Celsius and 1 atmosphere pressure. You'll find, remember we were talking about diatomic? Well, here's bromine, which is diatomic. Hydrogen is diatomic, nitrogen is diatomic, oxygen diatomic, fluorine diatomic, chlorine diatomic. 2, 3, 4, 5, 6. And guess what? There's one more hydrogen that's diatomic. There are only 7 elements that are diatomic. Everyone else is monatomic, if you will. They're okay by themselves. They don't need 2 of them. All right. This table here kind of summarizes everything. Now, hydrogen, one thing to know is hydrogen is way over here on the left side. We're going to learn later on that this is the side of the metals, but hydrogen is not a metal. So everything in yellow are gases. And then we got bromine and we got mercury right here. That are the 2 liquids. And everything else in blue are metals. So you can, even though you don't have to memorize all the physical properties of every element. If you got these points here where the liquids are, and you know that these are gases. If they ask you, chrome, is it a solid at 25 degrees? Yeah, there it is. It's all solid. You got higher chances of something with the element being a solid because there's so many of them. Okay. All right. Now, those diatomics, something to help you out, have no fear of ice cold beer or beverage, whatever your preference is. And the H of have represents hydrogen, N represents nitrogen, F represents fluorine, O represents oxygen, I represents iodine, C represents chlorine, not carbon. That pops up that C represents chlorine for the diatomic elements, and B represents a bromine. They're diatomic because at 25 degrees, they're not very stable. They actually need another one to be stable. Okay, only 7 of them. Some properties about there's 3 types, the properties of the elements. There's metals, non-metals, and semi-metals. Okay, and we can use the periodic table to determine who's who. All right, now non-metals are located on the far right of what we call the stair step. If you look at your periodic table, you got a little stair step. I'll show you that in a second. Semi-metals are the ones touching the metals, and the metals are to the left, with the exception of the hydrogen. Okay, now remember, semi-metals are those elements that have properties of both the metals and the non-metals. They're like the mule. They got properties of a horse and they got properties of a donkey. Okay, and this periodic table demonstrates where they're at. Okay. First things first, hydrogen is a non-metal. And it's way over here. You would think it is in the metal category, but it's not. It's hydrogen gas. The stair step is this. If you look, it starts with boron. If we go diagonally, we go across like this, and then we go down, and then to the right, and then down, and then to the right, and then down, and then to the right. And I believe 117 is a new one, but I believe that's going to be on the metalloid too. So that's our stair step. Okay. Basically, if you look at the periodic table, let me share that again. See that stair step right there? Okay. That is where we define metals and non-metals. Because we use that reference point Oh my goodness, where'd it go? There it is. Okay. So you can, at a glance, by looking at the product table, you could be asking, okay, element number 30, is it a metal or non-metal? Well, it's to the left of the stair step, definitely a metal. Solid, I should say. It's a solid and a metal. Okay. Number 9, fluorine. It is a gas for one, plus it is a non-metal. Now, why do we want to know this? Because this is going to help us define what type of compound you have. Of all these combinations of elements that we can put together, we only got 2 types of compounds. It's a ionic compound and what we call a covalent compound. We'll talk more about that in a bit down the road here. But a ionic compound is a combination of a metal and a non-metal, like sodium chloride. Okay, sodium chloride is an ionic compound. Here's the formula: sodium chloride. Okay, we have sodium, which is a metal, and we have the chloride, which is a non-metal. This is an ionic compound. Being an ionic compound, when we talk about bonds, we think of those as 2 magnets coming together. They attract to each other. There's no sharing of electrons. If we look at a compound with, let's say, 2 nonmetals like carbon dioxide, carbon is a nonmetal. Oxygen obviously is a nonmetal. We have what's called a covalent compound. When they make bonds, they share electrons and they have totally different properties. Okay, so we're knowing who's a metal, who's a nonmetal, and then looking at the formula will allow us to categorize it as to either being ionic or covalent, which then progresses on to give us a whole bunch of lot more properties concerning that particular compound. Okay. So metal general properties, they tend to be shiny. Okay. They are such that their properties, you can smash them, you can stretch them out, hammering them. Back in my days of research development, I used to work with copper plates, 1/4 inch. And the way they were produced, they started with a billet of copper, which was about 3 to 4 feet thick, maybe about four feet width, and maybe about 6 feet long. That whole thing was run through rollers and heat and rolled back and forth, and brought it all the way down to 1/4 inch. So that's the property of metals. So you can stretch them out. All of them except mercury are solids. So mercury used to be used quite a bit for thermostats. Not so much now. We're getting now into digital systems, but generally the density. Remember that ratio of mass over volume. Density is fairly high, and they tend to have a very high melting point. Okay, very high to get them to melt. They're very good conductors of heat and obviously electricity. In fact, anything that conducts electricity is a good conductor of heat. When we compare them to nonmetals, generally when they are solids, and there are a few that are, they have a dull appearance. They tend to be, if they're solids, brittle. A lot of them are gases, okay? And their density is low compared to metals. And they have a very low melting point, okay? They soften. And they're not very good conductors of ion, and therefore being bad conductors, they're better insulators, okay? All right. That's why you have if you think about it, if you have some double pane glasses, there's just air in between the 2 glasses because air does not conduct electricity, and hence they're very good insulators. Yeah. All right. So be able to look at the product table and at least be able to name the first 20 and the ones we gave you as far as their names are concerned. Be able to determine for any element whether it's a solid, liquid, or gas at 25 degrees Celsius. Okay. Also determined based on the periodic table. It's not necessary to memorize all the properties of all the 118, but be able to find it and then determine on the stair step its position relative to the stair step, which then would tell you whether it's a metal, a non-metal, or a semi-metal or metalloid. Okay. And then there's only seven elements that are diatomic. Be familiar with those 7 elements. Remember that C represents chlorine and not carbon. Okay. That being said, ladies and gentlemen, you are done with chapter 1. All right. Any questions on chapter 1? We used to wait for this chapter 1. We used to make that chapter 2, and we get into math skills at first, and then it just kind of put a dent on things. So we thought, well, let's talk about chemistry first, and hopefully get you excited about what's coming, and then we throw in the math. So anyway, as I stated before, the mathematics is not complicated. We're not doing calculus, differential equations, matrix algebra, nothing like that. Add, subtract, multiply, divide. With a little bit of algebra, being able to recognize that units cancel. Okay, so we're going to get into a technique of how to use conversion factors, which are nothing more than ratios with units. Okay, dollars per hour, that is a ratio. Miles per hour, that is a ratio that I can utilize. I can write it one way or the other. And then keeping track of my units as I set these up, that allows me to cancel the units. And I know almost 100%, 99.9%, if you follow this technique, that you set that problem up correctly. I don't give you 100% because I don't control that calculator that you're pushing. Okay, that's on you. But if you set it up properly with the units properly set up and you're following the units and canceling things out, you'll see that the problem is set up correctly, and you get to the answer that you're looking for. Okay. There's a lot of practice problems in chapter 2. Do them as much as you can. Don't forget about that sessions that Dr. Dana and Dr. Kim are offering. Feel free to go to those. Okay. Now, a measurement. Okay, it's simply a number, but more importantly, it is a number with a unit. Because if we just give a number, that doesn't mean anything. If you say a book weighs 8, that's meaningless. It could be 8 pounds, 8 ounces, 8 tons, whatever. But it's units. Units are important here. Now, keep in mind, we in science utilize the metric units. However, we're going to be using some English units here too, because we're going to be using these factors to convert from one unit set to the other to get you ready. As we set you up with this technique, we're going to be eventually doing calculations of chemical equations to calculate how much product, how much reactant we're using. And we're going to be utilizing the same technique using the units to help us follow through the calculations. Okay. All right. So in length, we generally use units like centimeter, millimeter, meters, and kilometers. Okay. Obviously, you're aware that this chapter deals with accuracy. Okay. Now, I'm sure you've seen this where you've done some calculations and your calculator popped out, 20 units, 20 numbers. And you might be tempted to report all those 20 numbers. But keep in mind, the whole thing about this chapter and the next chapter is that your answer for any calculation that you do cannot be more accurate than the least measurement that you did your measurement with. Okay. And we all know that there are differences, like these two rulers. We're going to have, you can see that the white ruler is not as accurate in reading than the brown one, right? And if I were to, let's say, take a mark here And let's say I wanted to, I don't know, measure the distance from point 0 to that red line using these rulers. You know, the white ruler, what would you guesstimate your best number would be for that? What do you think would be your guess if I were to measure from 0 to that red line using the white ruler? What's your best guess? You know, and I say guess, why? Because that last number is an approximate number. What could I say? Would you guys agree that maybe 2.4 would be reasonable, right? And notice I said 2.4 because you might see 2.3, and that's fine. But the point is, I couldn't get more accurate to one decimal place, right? Compared to the bottom one, because having more increments, guess what? I got 2.3, almost 2.4, and just above that red from my end, I can see 2.41. Okay. The point is, I can go up to 2 decimal places with the bottom ruler compared to the white ruler that I can only go to the 10th place. Okay. Giving me 2.40 using the white ruler would be inaccurate because you're not that accurate with the instrument. If I were to measure a room using a ruler versus a laser beam, obviously the laser beam is going to be a lot more accurate than a ruler. That's correct, right? But the thing to take away from this is this. If I were, for whatever reason, we're going to multiply or divide these two numbers, my answer could not be more accurate than the least accurate measurement, which would be the 2.4. I mean, I can go over here with a micrometer and just measure the heck out of this and go maybe 3 decimal places, and that's great. However, the accuracy of my measurement could not be more accurate than my least accurate measurement, which is 2.4. Okay. We can't give it accuracy when we don't have it to give, because we're limited through the tools. And the other thing is that every measurement has a degree of inaccuracy at the last decimal point, decimal place. Okay. Nothing is 100%. There's no tool, because even making the tool to measure, there's a degree in inaccuracy to make that ruler. Okay. Or we want to call it uncertainty. Grams of mass, we use the units of milligrams, kilograms, or G for grams. And you can, again, we got 2 different balances. We got a triple beam balance on the left and a digital balance on the right. The digital balance, if you look at the numbers, you can probably go about 4 decimal places as compared to the one on the left, probably 2 decimal places. And so obviously the digital balance is more accurate. But the same thing, if I were to use these 2 numbers and multiply or divide with them, I couldn't be more accurate with my answer than the one on the left, as far as the accuracy. Mass versus weight, I may have touched on this before, but we interchange the two because we're stuck on Earth here. All right. But there is a difference between mass and weight, and it is governed by the gravitational constant of the planet that you happen to be on. And so here on Earth, it's 9.8 meters per unit per second square, I believe. So, for example, if you weighed here 170 pounds on Earth, you're going to be about 28 pounds on the moon weight-wise. But your mass is going to be the same. Okay. Volume. Well, units of volume, we generally use a capital L, which represents liters. And then we use prefixes if necessary. We could have kiloliters or ml, one of the most common units, milliliters, ml. Those pieces of equipment on the right-hand side is generally some of the things you use in the lab to measure volume. Okay, syringes, you may know this, CC stands for cubic centimeter. And that's basically a measurement of 1 centimeter times 1 centimeter times 1 centimeter. Length, width, and height, you end up with cubic centimeter. Okay. which is equivalent to 1 milliliter. So 1,000 cubic centimeters will be 1,000 milliliters. Okay. Now for the English units, I always had trouble with quarts, pints, and everything. So this kind of helps me out a little bit. All right, we've got the big G here. Okay. That represents the gallon. Now within the big G, we got 4 Qs, which represents 4 quarts. So there are 4 quarts in a gallon. Now within the Q, there are 2 Ps, which tells you that there are 2 pints in a cup. And then within the P, there are 2 Cs, which tells us that there are 2 cups per pint. The point of this is you have 3 conversion factors. And these conversion factors I can write as a ratio. And so I have 1 gallon, I can write 1 gallon over 4 quarts. Okay. Or I can write it as 4 quarts over 1 gallon. Which one of these I use depends on the question being asked. Question might say, all right, if I have 10 quarts is equal to how many gallons? Okay, that might be the question. And so when I look at my 2 conversion factors, what I'm looking for, here's the key thing, what I'm looking for will always be in the numerator. So I'm going to use this one on top. Okay, so if I got 10 gallons and I multiply that by 1 gallon over 4 quarts. Okay. Oh, what did I do? It's supposed to be quarts. I got 10 quarts equal to how many gallons? I'm paying attention. Okay. Notice that my quarts cancel. Okay. Leaving me with units of gallons, which is what the question was asking for. Okay. And now if I reverse it and I say, okay, now I can say I got 10 gallons. How many quarts is that equal to? Well, I'm looking for quarts in units, and guess what? I'm going to use this one. So now I got 10 gallons, and I'm multiplying that by 4 quarts over 1 gallon. Okay, gallons cancel. Boom. Now you do the math, you got it. These are the kind of units, in fact, these ratios you need to set up, okay? Because down the road, when we get into chemical equations, we're going to do the same way to keep track of our units. And we're going to end up maybe setting up maybe 3 conversion factors. And by keeping track of our units, boom, we're going to get to the answer. I have an example that I'm going to utilize when we get to there. That's an extremely crazy example. But the point of that, yes, I want it to be crazy. The units made no sense at all, but that was the point. The point being, I can get from A to B. I can get from apples to bananas if I have a conversion factor and I set up my units properly. All right, so those are some factors for English units. Okay. Reading liquids. The thing about reading liquids, when we put a liquid into a cylinder, what happens is you form this meniscus, a concave kind of shape. Because of the properties of the liquid, some liquids actually go the opposite direction. But you form this meniscus, and what you want to do is you want to read at the bottom of the meniscus. Okay, this is where you're looking at, up in this direction. You gotta look up, look in that direction. Bottom of the meniscus, that's where you take the measurement. Now, thing about reading these, getting the correct number is, do note, this is called a graduated cylinder. Some cylinders or some liquid containers had their scale upside down. They may start at 0 up there, but always know which direction you're going. You know that 0 is down here, so you go in it from bottom up. Okay, sounds like a common thing to do, but it's surprisingly occasionally people misread this. They read from top to bottom, but even though the 0 starts at the bottom. So if you read this, you can see you're looking at 21, and the same scenario is 21 point, whatever you want to call it. You know, some people may say 21.5, and it's milliliters, right? You might say 0.6, but the point is that you can only go to the 10th decimal place because the number of marks in the graduated cylinder. Okay, there are some that got more marks, like the ruler we did before, to get a more accurate reading. But you're limited here to 1 decimal point place. Right, and remember just to read the meniscus, the bottom of the meniscus. All right, so this brings us to significant digits and significant figures, which can be a little bit
Dr.
confusing.
Fred,
Yes.
were you just saying a second ago though that sometimes the meniscus is like the other direction? Is that
Yeah.
what you were saying? So
Yeah.
then would you just read it from the top? Or
That's correct.
okay.
So if the liquid goes in the other direction, then just read the meniscus on top.
Okay, thanks.
Yeah, no problem. But the majority of menisci, I guess would be the correct term, would be concave shaped in the bottom that you'll see. All right. Which brings us to significant digits and significant figures. Earlier, I gave the example. I said, okay, it was like 21.5, and then it was like maybe, I don't know, 21.56. I got two numbers. I said, I cannot be more accurate than the least accurate measurement. And I said, well, my answer should have more than 1 decimal place. Okay, sometimes you can do that, but what we're going to do here, we're going to be able to define significant digits first, okay, and significant figures. Now, when we talk about significant figures, what we're talking about is, do they play a factor in presenting the correct value? We don't want to make the value more accurate than their measurements. And so sometimes it's not a straightforward, there it is. We have to first figure out how many sig figs we have. And this has to do it's not significant because of the value or lack of value. It's significant only having to do with the accuracy of your final answer. Okay. All right. So we talked about this earlier. I gave you that example. You can see these two here. So obviously you can see the top one. At the most, I'm going to get like maybe 29.1, maybe 21.2. That last number is a measurement. It's open to errors, uncertainty. If you see 0.1, that's fine. I see 0.2, that's fine too. That's why we call it uncertainty. You're neither correct or incorrect, unless you're like way out in left field someplace. The bottom one, again, a lot more example. We can go with 2 decimal places. Okay. So obviously the top one is least accurate. But we need to figure out the digits and figure out which digits are significant. Well, we got some rules here. I'm going to go through the rules and then I'm going to give you a shortcut. Okay. All right. Obviously, all the numbers 1 through 9, all the integers count. They're significant. Okay. Where the confusion sets in is when we start dealing with zeros. Okay. And we're gonna go ahead and do the rules first, and then we'll proceed with a shortcut, if you will. All right. When we look at a number that's less than 1, like this 0.0005454, the leading zeros don't count as significant. Okay. All they're doing is telling you the decimal point that they're at. So this number has 4 significant figures because the 5454 are all integers and they count. So there's only 4 sig figs here. Okay. Now you can see here very quickly while we're going through this. If I were going to multiply number 1 with number 4, my answer should have no more than 4 sig figs. If I were going to divide number 1 with number 2, my answer should have no more than sig figs because number 2 has only 4 sig figs and therefore the least accurate number. Okay. And this is true for multiplying and dividing only. Those are the examples I use. When we add and subtract, totally different rule. We'll get to that here in a second. So leading zeros don't count. Captive zeros, that is zeros that are between two integers, they count. So the number 3050, you can see that 0 between the 3 and the 5 does count, okay? But the 0 after the 5 does not count. So that number, 3050, has only 3 sig figs, okay? And the other example is 0.002001. The first 3 zeros are from rule number 2. They're leading zeros. And being leading zeros, they don't count. And then the 2 zeros between the 2 and the 1, they're captive. So they count. So that number has only 4 sig figs. Okay. And then we're going to do the final thing is here, trailing zeros. That's zeros after a decimal point and a number count, okay? And so let's take a look at the first example they utilize here, and where they have 0.0880. All right, these are leading zeros, so they don't count. If we take a look at the 0 right here, guess what? They follow, there's an integer in front of them, and there's a decimal point in that number. So they count, okay? If we look at this number here, yes, there's integers in front of them, but there's no decimal point, so those zeros don't count as being significant. So the rule is real straightforward, I hope. If they're integers, obviously they count. No question about it, 1 through 9. If they're trapped between two integers, they count, no problem, okay? The question is, when is it when they're not in those conditions? Well, question number 1, if you look at a 0, if there's an integer in front of them, that's a yes. You ask the question, is there an integer in front of the 0? The answer is yes. Is there a decimal point anywhere in that number? If the answer is yes, then those zeros count. If the answer is no to any of those questions, they don't count, okay? So try that on like we just did here. All right, so we look at these zeros here. Is there an integer in front of those 2 zeros? Yes. Is there a decimal point anywhere in that number? Answer is no, okay? So those zeros don't count. There's only 3 sig figs. If we take that number and we do this, ask the questions. For these 3 zeros, this one and this one, is there an integer in front of them? Yes, there is. They count. Is there a decimal point anywhere in that number? Yes, there is. Okay. So therefore, all the zeros count, and we have 3, 4, 5. We have 6 sig figs here. Okay. And so once we determine the number of sig figs and we are multiplying and dividing, let's say we're going to take this number with this number and we're going to multiply, we're going to multiply those 2 numbers. Our answer should have no more than 3 sig figs. Okay. Why? Because we cannot be more accurate than the least accurate number. So the number with the least significant figures is the least accurate number. And they're going to define how many sig figs your answer would have. Okay? And this is for multiplying and dividing. So we first have to learn how to determine who's significant and who's not significant. And again, significance is dealing here only with your answer and with respect to how many significant figures your answer should have. Has nothing to do whether that number is of value. Yes, of value, they play a role. Okay. All right. So the last part here, adding zeros, and for that number, we have 5 sig figs for 285.00. Ask the questions, you'll see you got 5 sig figs there. All right, now there are numbers that are exact, and therefore, being exact numbers, they don't play a role in determining what is significant. Okay. For example, you say any count, any like 14 people, 15 people, 100 people, those are exact numbers. You've got a conversion factor, 3 feet per yard. That is exactly 3 feet, even though feet is a measurement, but there are exactly 3 feet per yard in that conversion factor. Therefore, that number would not play a role in determining how many sig figs. 100 pennies per dollar, 5 iPads, a 12 pack, exactly 12 cans of beer. Okay. Anything that you measure, either the length, the weight, or the mass, any measurement is not an exact number, and therefore will play a role in determining how many sig figs you have. For example, if you measured something that was 200 pounds, but there's only one sig fig in 200, right? So your answer would be limited to, if you're multiplying 200 times, let's say 1.5, well, your answer would be limited to one sig fig. Okay. Anything that's measured is not exact. Now, another thing that is exact, we just went through the periodic table and we saw it on the surface, you would think, well, that's a measurement, the atomic weight, where we had a decimal number. But I'm here to tell you, make note of this. The atomic number you see in atomic weight is not to be used determining your sig figs, because that number is the average of whole numbers. And the average of whole numbers has an infinite number of significant figures. What do I mean by that? Well, what's the average of 4 and 5? 3.5, right? So I could write 4.5. What am I saying? 4 and 5. I got two numbers. The average of those two numbers is 4.5. So I could write that 4.50000000 to infinity. And that's what I'm saying. The atomic masses, the atomic weights, are the averages of whole numbers, and therefore do not use those to determine significant figures in your calculations. Okay. All right. So let's take a look at this one here. We have 5.05. Okay. How many sig figs do we have? You think we have 5.05?
Three.
You got 3, exactly. 1, if you forget about the captive rule thing, because that 0 is captive between the two 5s. If you forget about that, ask those 2 questions. You can't go wrong. Look at that 0. Is there an integer in front of that 0? Answer is yes. Is there a decimal point anywhere in that 0? Answer is yes. Therefore, it's significant. Therefore, we got 3. 1200 only has 2 sig figs, right? Those 2 zeros are just trailing zeros. There's no decimal point in there. If there was a decimal point, they would count. 0.02020, you can see that those 0.0 are the leading zeros. But if you forget, ask those questions again. No, there's no integer in those leading zeros. There's no integer in front of those leading zeros, so they don't count. You stop there. The 0 between the 2's, there's an integer in front of the 2. The other zeros, in fact, both the 0 in between the 2's and the trailing 0, there is an integer in front of them, and there's a decimal point in front of them. Therefore, they count, and you got 4. Okay. You got leading zeros there. You only got one sig fig. 50, again, only has 1. And you had a decimal point in zeros. Now all those zeros count. There's an integer and a decimal point in there, so they all count. There's 4. And then obviously 1, 2, 3.45. They're all integers. They all count anyway. And the last one has 3. Okay. So once we determine who's sig fig, and then we have to do some mathematical things. And if I were going to take this number and this number and either divide or multiply those sets of numbers, my answer should only have one sig fig. Why? Because this number here has only one sig fig, and that is the least accurate measurement. Okay? The least accurate measurement. And if both of them have one sig fig, if I were to do the same mathematical functions to these two numbers here, then my answer should have only one sig fig. Okay? Now, let me finish this one up because this kind of summarizes all that about the zero and the integer and the decimal point for you. It's just a quick summary there to help you out. But question is, well, how do I know? How do I round it up? I got to round this number up. Now, there's some rules. Some people have certain rules. Some other people have certain other rules. We're going to use the Chem 130 rule. Very straightforward. Okay. And we're going to look, we first have to look at that number that we're going to round. Either that number is going to stay the same or it's going to move up by one. Okay. And that is determined by the neighbor. Okay. By the neighbor of that number. If, for example, we have, I don't know, 12.57896, and then we want to round it off here at the at the four sig fig position, which would be the 7. We look at the neighbor only. We don't care about what's happening down there. Okay. And then we apply this rule. Is the neighbor less than 5? If it's less than 5, we leave the 7 alone. If the neighbor is greater or equal to 5, then we round up the 7. So this becomes 12.58 because the 8 there is greater than 5. Okay. Now, if, for example, you got this number, okay, and we want to round up right here the 0 to the 3 sig fig. This is 1902. That looks bad. Let me see if I can erase a little bit. I'll finish it up in here. We want to round it up here. This is very crucial here. Okay, we looked at the neighbor, which is the 2, and we apply the rules, and we can see that 2 is less than 5. So the 0 stays 0. Now, when you do that, here's the thing to remember. Any value, any numbers after the decimal point, we can get rid of. Okay? But any numbers before the decimal point, we can't get rid of. We want to, that 2 becomes 0. So we go like this. Look at the magnitude that you're in. You're in the 1900 range. Okay? And if I drop that 2, guess what I have? 190. Well, you changed the magnitude. You don't want to change the magnitude, right? You know, put a dollar there in front of a dollar sign, maybe put it in perspective. You're in the $1,900 range. So when I round it off, I don't want to drop that 2 because guess what? If I drop that 2, now I'm at $190 range. I changed the magnitude. So the point is, any numbers after the decimal point, don't care. Drop them out, get rid of them. Any numbers before the decimal point that are going to be dropped off, you need to replace those with 0. Okay. Okay, so that's what we're talking about, not the magnitude. So if you got to round the 1 into 1 sig fig, which is the first number, your answer would be 5,000, not 5, because 5 wholly changes the whole magnitude. You want $5,000 or $5? See what you did by dropping the magnitude there. Okay. All right. So I got 530. Why don't we stop it here? Make a note of this. Okay. Wow, it stopped at the same time, same slide as my last class.